Hi, everyone. It's Dr. Sheftall again with Truth in Science. Today's presentation is going to be quite a bit shorter because I asked for constructive criticism on my previous presentations, and everybody said the content was great, best they'd seen, but they were too long. So I am going to try to make my presentation shorter. Today's presentation is about SARS testing. It's a very, very important problem, and I'm going to move along, and you can always back the video up to look at something again if you didn't quite understand what I was talking about, because I try to write most everything out on the slide. So let's get started. Another thing that was recommended to me after the first presentation was that I have to put a bona fides type slide on all my presentations, just so people can understand what my background is in the subject matter that I'm addressing. And most of them for me are going to be mathematics, medicine, and some other things, some physics things, because I was a physics major. But I don't want to go through this necessarily. I just want to make one little point here, and that is that I put a picture of myself here at either age 20 or 21. I graduated when I was 21, but I can't remember what month they took the picture. And I'm 64 now, so that picture was taken either 44 years ago or 43. So at this point, you know, maybe the school that you went to, or maybe some scores on tests that you achieved back then don't really matter anymore. It's more about your argument, which it always is, of course, even when you're young. But again, I can see the reason why people told me to put these slides in, but my argument has to stand on its merits. That's what I want to say, and then same with everyone else. Oh, by the way, this SAT score I took about a year and a half ago, and I just wanted to find out how it had changed, because I took it back in the 70s, and didn't prepare for it because I just wanted to know what had changed so I could help some students who are interested in learning a little bit more about it from over here in Asia where I live, because they want to go to school in the States. So I said, I'll go over some questions with you, and took the test. Okay. Let's see. Okay. The first thing we're going to talk about is a very important test called the PCR test. And this is the one that's used when you're watching the news and you see how many new cases they found today, or how many deaths they found, or how many hospitalizations. So it's a very important test, but there's some real problems with it, and I'm going to go over those. First, I need to define all the terms clearly. The RT-PCR test stands for reverse transcriptase polymerase chain reaction. Reverse transcriptase is the enzyme that takes RNA to DNA. And this is done in this case because the SARS-2 virus is an RNA virus, but the chain reaction part of the test requires DNA. Polymerase is an enzyme that assists in copying DNA or RNA. They're used as templates, and the enzyme polymerase, as the name suggests, takes individual nucleic acids and forms a polymer with them. And DNA and RNA are polymers of nucleic acids. DNA is deoxyribonucleic acid, and RNA is ribonucleic acid. Because of the specificity of how the base pairs attach, that allows you to make an exact copy of the template. Now, this is the chain reaction part. So now we've defined all the terms, and let me just say a couple things about chain reactions. Everybody knows what they mean when we're talking about a nuclear reactor, for example. And it's the same thing here. There are 2 copies here. There are 4 copies here, which is 2 squared. 2 to the 3rd power is 8. So there's 8 copies here, 1, 2, 3, 4, 5, 6, 7, 8, and on and on and on. Each one of these steps is called a cycle. And in the United States, they go up to 40 cycles. 2 to the 40th power is 1 trillion, which is 1,000 billion. And therein lies one of the big problems for the test. Now, this test is used to count new cases. also to count hospitalizations due to SARS or even deaths due to SARS. And the question is, how many of those are being mislabeled? We don't know exactly, but we know it's a large fraction. The problem is the test is taking a very small amount of RNA that could be in your nasopharynx, okay, after you long recovered from the illness, but the test will pick that small fragment up and amplify it so that what you have is large enough to perform chemical tests on, such as, is the virus there? You need a decent amount of it to perform that test. I'm sorry, or is the, God, made the obvious mistake. Not is the virus there, but is RNA there? And so you need a lot of RNA to determine if you even have it there, believe it or not. Okay, so my assertion, and it's going to be a little bit controversial, is that we should stop testing asymptomatic low-risk patients. The reason is the results we get are so misleading, and I'll get to that in the next slide, because the test is testing for RNA, not the virus. And you can have the RNA long after you've recovered from the virus. All right. So again, this is just going to reiterate the same thing I just said. After amplification, what was originally an inadequate sample is present in large enough quantities to perform chemical tests, such as, is the RNA virus, excuse me, is the RNA present? Okay, and remember, these tests are done by swabbing either through the nose to the nasopharynx or through the mouth. Maybe they swab the tonsils or something. Okay. The test is not measuring viable virus. The only way to do that would be to culture the specimen from the nasopharynx and see if virus grows out of it. Just finding a little RNA segment, which can sometimes be there months after you've recovered from the illness, does not mean you have found a new case. And yet on television all day long, they're quoting the number of new cases they found based on this test. And that is a real problem. Because here's why it's a problem. It engenders fear in the population because we think, oh no, there's this enormous wave coming where we're all going to be doomed, you know. And then what happens is, like I said in my last video, which lasted 4 hours and went over every single aspect of SARS. If you want to watch it, it's called Stop the SARS-2 Stupidity, Please. But what happens is the public gets in a state of panic and fear over this. And it's easier to make them accept a draconian, very ill-advised policy like a lockdown. Lockdowns did not help, and they caused enormous damage to the population. People lost their jobs, their health insurance, their livelihood, in many cases, their life savings. And in many, many cases, well over 150 million people will lose their lives because of it. And right now, worldwide, there are only 1.4 million people who have died of SARS-2. Not to minimize that. It's horrible if you get it and you get sick from it. But the fallout from lockdowns is much worse, on the order of 100 times worse. This is a picture of a viral culture, by the way. Okay. Now, I just watched a YouTube video of a very attractive, very intelligent lady doctor who said, quote, "The RT-PCR test is used to determine when a patient is currently infected." This is completely wrong. Is all the RT-PCR test does is find out if there is virus in the person being tested. Oh, sorry, I did it again. Oh, God. Oh, it's easy to do this, I'll tell you. They're only trying to, the test only determines whether there's RNA in the person being tested. Sorry, I keep saying the same thing. Now, that's a very important thing to know if you're dealing with, say, a rape case or something. it's good that we're able to amplify the RNA and see if it's in or on the victim. Very, very valuable test. But as far as this illness is concerned, the SARS-2 illness, it is very misleading, okay? So I made myself a little quote here. You can take a tiny, meaningless fragment of a molecule and amplify it into the end of the world. And that's what they're doing. Now, let me just say a little something about the so-called second wave. Saying that something is a second wave or a third wave, I've heard even, is a little bit, it sort of displays a misunderstanding of the virus. You know, when you look at a Gompertz curve, which is the curve that we see with time of the cases or the deaths, you have to ask yourself why the curve turned and went down, okay? And the reason is because the virus had trouble finding more victims, if you will, more susceptible people after it had swept through the population in a very natural process. And then, you know, there's another hump, which we will see this winter, and we're already seeing it, of course, and that's 100% valid. We see this in cases and deaths, not to the degree that they're publicizing on television, of course, because of what I'm talking about now. But even when a virus has essentially run its course, like you might see in New York, if you look at the graphs, or the Scandinavian countries, or many countries, the Northeast of the United States. The reason, okay, let me just stick with the subject so I don't get off on a lot of tangents. You see that the virus has run its course, say in the state of New York, okay? Because the virus itself couldn't find any more patients or any more people to infect, and so it fizzled out. Now, there is a slight resurgence in the winter, but that's seasonal. I wouldn't call that a second wave, you know, like some mysterious reason the virus woke up and is killing people again or something. This is a seasonal virus, just like the flu is. That's why we have a flu season, okay? Just like colds are seasonal. All right, and there's a lot of reasons for that. The dryness of the air, the temperature, the closeness, people tend to huddle together when it gets cold, all that's part of it. But another part of it is when a virus sweeps through the population, let's say it swept through in March and April in the Northeast, a lot of susceptible people succumb to it, and you'll see that if you look at the graphs. But some people don't, okay? Some people are just healthy enough to survive it. And now we're in the October, November, December time range, and those people who were just healthy enough to survive it back in April are 6 months older now. And if those people who are 6 months older and 6 months sicker, by the way, you know, if the person's 30 years old, 6 months doesn't really mean that much to their health. But if they're 85 years old, it might be half of the rest of their life, or 1/4 of the rest of their life. So 6 months is a long time if you're very old and things are kind of falling apart. So let me just go back quickly to, if you take a person, an elderly person, or even sort of an unhealthy 50-year-old or 60 or 70-year-old, that person may not have gotten infected back when the virus swept through, let's say, New York. Now they're 6 months older and sicker, if you will, okay? So they may, if they catch it this time, they may very well succumb to it. I don't really think that should be considered a second wave, okay? That's just a seasonal effect of them being slightly more likely to be infected in the winter, and they get infected in the winter and they succumb, and so their data point goes on to the deaths, sadly, okay? So just think this through a little bit. There's a reason why all of this happens, but you have to be real critical in your thinking. And what upsets me so much is that I don't blame the general public. You know, they're going to the doctors and the experts to find out about this, but the experts have been wrong on almost every call so far. They put us into lockdowns, which didn't help at all. It was an idiotic idea. And the reason I can say that confidently is because I wrote an essay back on March 15th, before we even went into lockdowns, explaining why lockdowns would not work. And the fundamental reason is because a lockdown is a macroscopic solution to a nanoscopic problem. The virus is 1/4 of the virus diameter is 1/4 the length of the shortest wavelength that we can see with visible light. So the viruses are invisible, and it's not some hocus pocus definition of invisible. It's just kind of meaningless. You cannot see them with a light microscope. You have to use an electron microscope to see them. Okay, without getting deep into the physics there's a lot of reasons why the evidence, the proper studies that have been done on masks have all shown that masks don't reduce the transmissibility. That doesn't mean you shouldn't wear a mask sometimes. I'm a surgeon. If I have to intubate someone who has COVID, SARS-2, while they're awake, I'm going to put a mask on and maybe even a shield if it doesn't damage my vision, because the patient's going to be fighting me and coughing and spitting on me while I'm doing the intubation. But as far as mask mandates are concerned for the general population, they don't work. It doesn't reduce the transmissibility. I looked at 72 years of randomized controlled trials, and in every single one of them, they made a statement that the masks, even though they thought that they would help, did not reduce the transmissibility. And even this year, we've had one similar study. It's called the Denmark study, casually. And that study also showed that there was no significant difference in mask wearers versus people who did not wear masks. So we're near the end now, and I just want to point out something that's fascinating, and in a way it's shocking. Let's say that you get a PCR test and the result is positive. You go into the hospital or your doctor's office, he does the test, and he tells you that the test is positive. What are the chances that the result is wrong, that you really don't have the virus? Okay. Now, let's say that you now let me just say this first. The key variable here is the false positive rate. And I've studied this I've researched this extensively and come up with a range from experts. And the range runs from 1% to 8%. And I've looked everywhere to see if there's any more differences. Almost all of them are right around 5%. So what I did was, on this analysis, I did a calculation for 8%, 5%, 3%, and 1%, just to sort of show you that I don't want to be, I want to be complete and make sure everyone, if you're on the 1% end or the 8% end, I did the calculation for you. Okay. So let's look at this. Let's say you test 100,000 people and the prevalence in the population is 1%. That means that 1,000 people have the disease, okay, and 99,000 do not. That's a prevalence of 1% in the population of 100,000 that you're testing. Now, let's look at these people who actually have the disease first. We know, and it's very well accepted now, agreed upon, that the false negative rate is right at 25%. So if you take 25% of 1,000, you'll get 250. And remember, a false negative is someone who gets a negative test, but actually has the virus, okay? That's why it's a false negative, okay? So 25% of 1,000 is 250. If you take 250 away from 1,000, you're left with 750. And that is the number of true positives, people who had a positive test result and have the virus, okay? Now, we're going to use 8% in this calculation. So 8% of those who do not have the virus is 7,920. Okay. Now, those would be the false positives. Those are the people who get a positive test, like I'm talking about up here, along with the true positive. That's part of this also. But the false positives get a positive test. It's false, though, because they don't have the virus, all right? They're not infected. That's why it's called a false positive. Okay, and if you subtract 7,920 from 99,000, you get 91,080. Okay, those are the true negatives. The people that get a negative result from the test and also are not infected. Okay. Now, if you want to know what the chances are that the result is wrong, you have to divide the false positives, meaning a wrong result, by all of the positives. And all of the positives are represented by the true positives and the false positives. So the equation is false positive divided by true positive plus false positive. That's how you will determine the percent of positives that are wrong or false, okay? So look at this. We said 7920 was the false positive number. So it's 7920 divided by the true positives, which are 750, plus the false positives, which is 7920. And when you do that and add these and then do the quotient here, the answer is 91%. Isn't that shocking? It just surprised me. I didn't know it was that bad of a test. 91% of the people who receive a positive result from the test got the wrong result. Okay? Think about that. The result is wrong in 91% of the people who have the test done and get a positive result. Okay? So let's change the false positive rate here and sort of satisfy everyone that's in the 8% camp, the 5% camp, the 3% camp, or even the 1% camp. Again, the consensus is around 5%. If the false positive rate is 5%, there's an 87% chance the result is wrong if you receive a positive test. Result. At 3%, there's an 80% chance the result is wrong. And at 1%, even the lowest, the extreme lowest end of the expert opinion, let's say, there's still a greater than 50% chance that the test is wrong, the result is wrong. Isn't that amazing? I was real surprised. Now, the other kind of tests that are done, and these are not as important for a lot of reasons. They're not very accurate either, but they do need to be addressed in this little presentation. Antibodies testing. I wrote some sort of facts about antibody testing here in antibodies. And if you watch the previous video, the 4-hour one, I gave everyone a very thorough primer on immunology. So they'd understand all this issue about T cells, B cells, antibodies, T helper cells, T killers, natural killers, dendritic cells, macrophages. There's a lot of players involved in the immune response that you need to know about, because in order to talk about this stuff, having not maybe gone to medical school, it's difficult to talk about it if you don't know a little bit about it. And I think that's part of the problem. You hear the anchors on CNN who all majored in journalism or communications or political science or something like that, talking about this scientific stuff and just saying the most bizarre, misleading things to the public. And the public watches TV. And with that enormous forum that they have, platform, they really should not be talking about it. Even, well, I'll leave that alone for a second. But unless they know what they're talking about. Now, if they do, I'm all ears. I want to hear everybody's opinion and everybody's reasoning. Because again, it doesn't matter what degrees you have or what your name is or how good your idea was. If it doesn't match with reality, the guess is wrong. Okay. Okay. So, and that's a summary of a quote by Dr. Feynman, which is a great quote. And I read it verbatim in the last video. So anyway, let me just say a couple things about antibodies that are very important to know. They're made by the B cells, and they're present in your blood, and they tend to decrease with time. If you measured 500 people and got the percentage of those 500 who had antibodies in their blood for SARS-2, let's say it's 7%, and you measure that same 500 people several months later, it'll be lower than 7% because antibodies are molecules like many other things, they're protein molecules, and they have a half-life, and they will decrease, the count of those will decrease with time. And that's one of the problems with antibody testing, by the way. The number of antibodies in your blood can be a little bit too low to turn the test positive, even if you're completely protected from the virus because of antibodies. If you go back and look at the immunology primer, you'll learn that there are two arms of B-cell immunity. One is the effector arm, in which the B cells differentiate into plasma cells, which produce the antibodies. And the other arm is the clonal expansion arm for memory. So just because the number of antibodies in your blood have gone down a little bit with time and the antibody test turns negative, it doesn't mean that you're not completely protected by clonal expansion and B-cell memory. So let me just tell you how the test is done, which will bring up lots of ideas on how inaccurate this thing can be. Over here we have, I call it a muffin tray, but it's a little plate with bays in it, okay? And looking at a cross-section and magnification of one of those bays, you see that antigen is put on the wall of the bay by the company that manufactures the test, okay? Then they wash the patient's blood over. This is a very basic explanation. ELISA stands for enzyme-linked immunosorbent assay, by the way, which sort of tells it all. But I'll show it to you in pictures here. So the patient's blood is washed over this bay that has antigen stuck to the wall. And some of the patients, if the patient has had an antibody response to the viral antigens, which are in red here, some of the antibodies that patient produced will stick to the antigens. The FAB portion of the antibody will attach to the antigen, okay? Those are the blue antibodies. Those are patient antibodies. Here we have another wash that is sent over this bay. And in this wash, there are antibodies to the FC portion of human antibodies. That's the constant fragment down here. Maybe these are made in an animal or something, where human antibodies would be considered not self. And so the animal would make antibodies to the human antibodies. But those animal antibodies have been tagged with something that's very easy to see. Maybe it's a biofluorescent molecule, okay? And so what happens is you get the bay now with antigen, which were put on by the manufacturer, human antibodies, which were attached in the first wash, and animal antibodies to the FC portion of the human antibodies, but on those animal antibodies is a visible marker, okay? We call it a tag. So when you look at the tray again, the muffin tray, you see that yellow begins to appear or appears in the various bays. And depending on the titer and some technical things, this might be considered a positive test. It probably would be, okay? So that's how the ELISA test works. And you can imagine how many ways this can go wrong. For example, maybe the patient's antibodies are not in great enough number to attach and make this turn yellow enough to be considered a positive test. That's one problem. Maybe there weren't any blue antibodies, if you will, patient antibodies at this stage, but they sent the animal antibody wash over the bay and nothing attached to blue antibodies because they're not there, but maybe some of these antibodies sort of accumulated on the bottom of the bay for some reason, and then you look in the bay and it's yellow and you think it's positive. So there are many, many ways this can go wrong. This test is notoriously inaccurate. So there is the presentation for today. Thank you very much for watching. Please visit my Patreon page and consider becoming a patron so I can continue to produce quality. Truth and science is the tagline for my page on Patreon. So please do consider it. And thank you very much for watching, and I'll see you down the road.